Imagine, out of boredom at workplace, you decide to hop on a spaceship headed to the Andromeda galaxy. Sounds exciting, right?
Yeah!
But hold up. Before you start packing your bags, let me break it down for you. The distance to Andromeda galaxy from Earth is about 2.5 million light years. That's like 2 followed by 19 zeros worth of kilometers. And to make matters worse, special theory of relativity prohibits the spaceship from traveling at or more than the speed of light. So it appears hopeless to even hope for reaching anywhere near the Andromeda galaxy in absence of exotic sci-fi things like warp drives or wormholes. But remember, hope is a good thing, maybe the best of things, and thanks to Einstein's theory of relativity, there is really hope. So buckle up, because things are about to get a little bumpy with some math involved. But trust me, the result will surprise you. Now let's put the pedal to the metal and hit relativistic speeds. Who knows, maybe you will be sipping on Andromeda's version of welcome drink sooner than you think. Let's start by setting up the space-time equations for the relativistic rocket continuously accelerating at 1g along the x-axis, which is comfortable for its passengers who will simply feel the equivalent of their weight on Earth. Now, to work with acceleration in the framework of special relativity, we need to consider a series of momentarily co-moving inertial frames, one for each instant having the same instantaneous velocity as the accelerating object. Suppose at any instant t in Earth's frame S, the velocity of the spaceship is v. We define at that instant a momentarily co-moving inertial frame S prime that is moving with velocity v with respect to Earth's frame. The rocket is at rest in S prime frame at that moment. In relation to S prime frame, suppose the rocket's velocity increases from 0 by dv prime in an infinitesimal time dt prime. The rocket's acceleration relative to this co-moving frame is then dv prime over dt prime, which is known as the proper acceleration, that is, the acceleration that the rocket and its inhabitants experience when they are at rest in S prime frame. We consider the proper acceleration to be a constant denoted by a. If dt is the time elapsed on Earth corresponding to the time dt prime in the co-moving frame, then these two quantities are related by the principles of relativistic time dilation. The increase in velocity dv of the spaceship with respect to the Earth's frame during the time dt then can be calculated as per the rule of addition of velocity using the relation between dt and dt prime. In the limit that dt goes to 0, dt prime also goes to 0, we get the expression for the acceleration of the spacecraft with respect to Earth's frame, which can be integrated and rearranged to obtain v is equal to at over square root of 1 plus at over c squared. So, with a equal to 1g, the spaceship will be traveling at relativistic speeds for most of the journey with velocities of approximately 0.7, 0.9, 0.95 and 0.97 c after 1, 2, 3 and 4 years respectively, and so on as shown in the graph. Therefore, various relativistic effects will be in play for majority of the journey. One such effect that we are concerned about here is the time dilation. With the help of the clock postulate, the expression for time dilation can be used to relate the time tau elapsed in the rocket's frame to the time t in Earth's frame. Armed with this, we can determine the distance the rocket travels in time t in Earth's frame from the expression for v by simply integrating, which in terms of spaceship's time becomes x is equal to c squared over 8 multiplied by cos hyperbolic a tau over c minus 1. So, with a equal to 1g, the spaceship will cross about 0.56 light years in 1 year of its own time, 2.9 light years in 2 years, 28.9 light years in 4 years, 1839 light years in 8 years, and 113,000 light years in just 12 years of its own time, which is larger than the diameter of the Milky Way galaxy. After approximately 15 years, the spaceship will finally reach the Andromeda galaxy, which is about 2.5 million light years away from Earth. That was sooner than expected, right? As you might have guessed, the trick here is performed by time dilation, which causes time to pass very slowly on the rocket as compared to that on Earth, so that in 2.5 million years on Earth's frame, the rocket and its inhabitants just aged 15 years. If you want to reach your cosmic destination, stop there and want to come back to Earth, you can follow a possible course by accelerating at 1g until you reach the halfway point to your destination. Then turn the spaceship around to decelerate at 1g so that you come to a stop at the destination. After that, you can turn the engine on again and repeat the same course to get back to Earth. Due to the symmetry of the motion, the time it takes you in the rocket's frame would be nearly 4 times the time required to reach the halfway point of your journey. The time needed for a round-trip journey to the Andromeda galaxy would be only 57 years. However, when you return, you will come back to a vastly different Earth in the future, one which might even be uninhabitable.